what is the center of mass? If you're dealing with a two-dimensional shape like a plate, you may want to know where to balance that plate on your finger. If the plate doesn't have uniform density, it may not be obvious where to balance it, right? And the center of mass is exactly that point. It's that point where you would want to balance it. It's also, if you think about in 3 dimensions, if you think about meteors, if you've ever seen pictures of meteors in outer space, they're spinning around in 3 dimensions, and they're usually spinning around more than one axis. They're always spinning around a single point, though. And that point that they're spinning around is the center of mass. Let me start with a very basic example where we do everything in one dimension. So in 1 dimension, imagine, I think a good example of this would just be a teeter-totter on a playground or a seesaw. It's just a plank balanced on what they call a fulcrum. The fulcrum is the balancing point, which for a teeter-totter is going to be right in the middle. But imagine that 2 children come and sit on this teeter-totter. Now, if they have equal mass, how do they balance the teeter-totter? Well, of course, they should sit equidistant from that balancing point. So if their masses are the same, M1 and M2 are the same, they would balance themselves just by sitting equidistant from here. This balancing point is what we're going to call X bar. And that is what we also call the center of mass. If one child is bigger than the other one, weighs more, then this picture is going to look a little bit different. Well, let's suppose the lighter child sits down first. So let's say M2 looks like this, and he sits down at the very end of the teeter-totter. Now, if the larger child comes by and sits in the same position on the other side, what's going to happen? Well, of course, the teeter-totter is going to tilt down in his direction, right? Because he weighs more. Just makes sense. But he can move on the teeter-totter to correct this, right? If he weighs more, what do? You move towards the fulcrum. So the larger child here, M1, will sit closer to the fulcrum to balance this. So again, the center of mass, it's the balancing point, but notice it's not equidistant to these 2 masses. What we find out here is we can treat the influence that these masses have on the situation just like torque, when we talked about torque way at the beginning of the class. If you remember, if you are tightening a bolt and you use a wrench to do it, you know that the further out you push down on this wrench, the more torque you generate, the easier it is to twist this bolt. And we learned that to compute the torque, you take the cross product of the force with this radial vector here, R. And torque was equal to, oh boy, I forgot if it was F cross R or R cross F. Well, I'll put a little question mark here because I don't remember exactly. I think it was actually R cross F, but I might be wrong. You should go check that in the book just to be sure. But it's essentially, you take the cross product here. And that gives you a vector coming out in 3 dimensions, coming out in the other direction. That determine the magnitude of that vector is the amount of, essentially the amount of twisting force that you're applying to this bolt. Now there's more to it than that because the angle that you apply the force to comes into play here. If we were measuring the wrench, I should have drawn the picture like this with the wrench horizontal, then that angle doesn't play a role because really, if you remember, the magnitude of the torque is the magnitude of it's the length of R times the length of F times the sine of the angle here, where the angle was this angle here. But if in the case where the wrench, if you're pulling directly down on a horizontal wrench, the sine of that angle is just 1, so it doesn't even play a role. And so you really are just multiplying the length R times the magnitude of the force F, and that gives you the torque. And you know, the longer the wrench you have, the more torque you're going to apply. Well, what's force? Force is mass times acceleration. And in this teeter-totter business, the acceleration due to gravity is constant. It's the same for both masses. So that doesn't really play into here. So really, the influence that each mass has is just, the force is just, essentially boils down to just the mass. And the torque that that person exerts is just the mass times the distance they are from the fulcrum. Okay, so you're going to find the influence of this mass, you're going to multiply it by the distance they are from the center here. So what we need to have happen for this to be balanced is that we need mass 1 multiplied by the distance here. Suppose this guy is at position x1. We need this mass 1 times this distance, that's absolute value x1 minus x bar, to be the same as the torque of this kid. So that's going to be m2 times his distance, x, the distance between x2 and x bar. If that equation holds, if these two sides are equal, then the teeter-totter will be balanced because they are exerting the same torque on the system. All right, well, I'm going to just unfold this equation a little bit so we want to get a formula for x bar. Or we want to solve this for x bar. Okay, so x1 minus x bar in absolute values is really just x bar x minus x1 because x bar is bigger than x1. So I'm going to write this like this. And x2 minus x bar absolute values is just x2 minus x bar because x2 is bigger than x bar. So we multiply through here. We got. I'm solving for x bar, so let's move the x bar terms to the left. Let's move the non-x bar terms to the right. Let's factor out the x bar. And I'm going to write this in order. So I'm going to write m1 x1 plus m2 x2 over here. And now I'm solving for x bar, so I'll divide through by m1 plus m2. Okay, so there's our formula for the center of mass. In the bottom, we have the sum of the masses. That's the total mass. And that's in the denominator. In the numerator, we have what they call the moment. Now, it doesn't matter how you've positioned the coordinate system here. I could have the 0 sitting over here. I could have, my x-axis could be that, or I could have the x-axis with 0 over here. Or it doesn't matter what numbers I assign. It's kind of all relative. And so that doesn't even play a role. As long as you fix coordinates up there, however you decide to fix them, you could just run this formula, and this will be the center of mass with respect to that coordinate system. And this will give you the center of mass. Right? This is a one-dimensional situation. And this is also a situation where we just have two masses, but you know what? If you work it out for more than two masses, suppose we had a whole bunch of children jump onto this teeter-totter, same formula works, right? So you'd have each child, you'd take their mass and multiply by their position, and then you'd add them all up. And then you'd divide by the sum of all the masses. That's the moment. And that's the total mass, just the sum of the masses. And we can even generalize this even further. We can imagine not just a finite number of children on here, but you could imagine a bar trying to balance a bar whose density varies as we move across the bar. So maybe it's really thick and dense on one end, and then it's very thin and light on the other end. Well, you can imagine this kind of like the same problem where at each point on the bar, you've got a different amount of mass, right? Because it's different densities as we move throughout the bar. And so now it's like having an infinite number of children sitting on this object, each one with slightly different mass. And so we can think about that situation. And so we would say that the density is a function of your position on the bar. So I would call that rho of x. Rho is usually what we use for density in physics. So the rho, this is the Greek letter rho. and it looks like a P with a curly tail. Right? So the density depends on x. This is the linear density. So it's the density per unit length. So it's the amount of kilograms per centimeter. All right, so if you want to get back to the mass, what we would do is we'd multiply the density times the small amount of distance. So if you take kilograms per centimeter, you'd multiply by centimeters, you get back to kilograms. So we can get back to mass from density just by multiplying by length. All right, so the picture looks like this. We've got this bar. Now, I'm not putting this in the center because maybe the bar weighs a little bit more over here than it does over here. It's more dense here than there. Right? So we imagine an x-axis down here. Doesn't matter where we position it, where 0 is, does not matter. What we're going to do is for each x, we're going to look at the infinitesimal mass at this point over here. Infinitesimal mass, because we're doing this over an infinitesimally small length of the wire, is going to be the density times an infinitesimal length. Well, that infinitesimal length, we call that, in calculus, we call that dx. So you imagine a little tiny little length that what we're going to do later is going to take the limit as that length goes to 0. And that's what makes it infinitesimal. Right? So it's going to be the mass multiplied by dx. Sorry, the density. I may have said the mass is going to be the density multiplied by the infinitesimal length. So kilograms per centimeter multiplied by centimeters gives you kilograms. So that gives you the infinitesimal mass. And so what we're doing is we're adding up all these infinitesimal masses. That's what this formula is saying to do. Add up all those infinitesimal masses, and that should give you the numerator here. Well, when you add up infinitely many infinitesimal parts, that's called an integral. That's what an integral is. It's just adding up infinitely many infinitesimally small things. So what does this become? The center of mass, therefore, is the integral of, look what we did up here. We multiplied the mass times x. Well, how are we getting the mass? It's rho of x dx. So we're going to multiply this by x. So really, we're integrating x times rho of x dx. Rho of x dx is the mass, and then x is the position from the center. And then we're going to divide by the total mass. How do you get the total mass? Well, you just add up all the infinitesimal masses. But we're adding up infinitely many of them, and they're infinitely small, so this is the integral of the infinitesimal masses. So this down here is the total mass, and this up here is the moment. And this is how you do this for a continuous problem, where the density continuously varies across the wire. So let's do an example. It's always good to do examples to make sure we fully understand what we're talking about. So, example. What I'm going to do is say that the density of a wire is given by x minus 1 squared, and the wire extends from -2 to 2. Okay? So what we're doing is we're looking at, on the x-axis, from -2 to 2, we've got this wire. It's extending from here to here, and it has varying density. This is actually called the linear density. Really, density is like kilograms per cubic centimeter, but here we're thinking about kilograms per centimeter. This is the linear density. So we want to find the center of mass. Where would we balance this wire? Center of mass. You have to excuse me, I'm running out of paper, so we're using old paper, which got some writing on it already, so you can just ignore that. Find the center of mass. Let's see. So here's the formula up here, right? So we've got our density. What we're going to do is we're going to multiply that by x to get our moment, right? So we're going to find the moment is going to be the integral from -2 to 2, because that's where this wire lives, of x times x minus 1 squared, x times rho of x dx. That will be, let's see, this will be the integral from -2 to 2. Let's see, this is x squared minus 2x plus 1. So this, when I multiply it by x, I get x cubed minus 2x squared plus x when I multiply that out. So then we anti-differentiate. Okay, so this is 2 to the 4th is 16, divided by 4 is 4. All right, so that's 4. This is 8 times, so 2 cubed is 8 times 2 is 16 divided by 3. And then 2 squared divided by 2 is just 2. And that's what I get when I plug in positive 2. When I plug in -2, I get, again, 4. This is going to be, is a negative and a negative make a positive. And then this again gives me 2 here. So the 4's cancel, the 2's cancel. So I really just have negative 16 thirds minus 16 thirds. So that's minus 32 thirds. That wasn't too bad. All right, that's the moment. We also need to get the total mass here. Well, that's just the integral from -2 to 2 of x minus 1 squared dx. If you work that out, you should get to 28 thirds. And so the center of mass is going to be the moment divided by the total. Moment of mass divided by the total mass, right? Well, the 3's cancel here. So this is just -32 over 28, which is -16 over 14. Just divide by 2 again, -8 over 7. -8 sevenths. Now, where does that look like? What does that look like in the picture? Well, it's somewhere, it's a little bit less than -1. So it looks like the fulcrum would actually be positioned right there. So it's very heavily weighted towards the left-hand side. Looks like there's a lot of mass in this region and not very much mass over here. And if you look at a graph of the density, you'll see that makes a lot of sense. Okay. So that's a linear density problem. We can also do densities. We could also find center of mass for like a plate, a two-dimensional region. Okay, so for instance, so what we have here is we have a triangular shaped flat surface, and I want to know, where do I put my finger underneath this thing to balance it on my finger so that it stays perfectly balanced? Where's that center of mass? Well, the trick to this problem is we have to break it down into two. We need to find the center of mass in the x direction, and then we have to find the center of mass in the y direction. Okay, so what we do is we imagine, take any point in here, right, some point xy. We know the density at that point, so we can find the infinitesimal mass at that point. So the infinitesimal mass at xy. Well, here, the density here for a plate in a two-dimensional problem, now it's not the linear density, it's the square density. Right? The square density is mass per unit area. So it's going to be like kilograms per square centimeter. So if I want to get back to mass, I'll multiply the density times area. Right? So the infinitesimal mass is going to be the mass at the point multiplied by dA. Instead of dx, the next step up, the two-dimensional version is dA. So we're imagining multiplying the density times a little chunk of area. And so the total mass is going to be given by integrating all these. You just add up all the infinitesimal masses. Well, that's going to be the double integral over that region of rho of xy dA. That's how you get the total mass. It's just same formula as before. We're just doing a double integral with respect to dA instead of a single integral with respect to dx. Now, here's the part that's a little bit different. I need to find the center of mass in the x direction. This is the x bar. Where do I put my finger in the x direction to balance this? Well, it's the same idea. We're just going to weight everything by its position x. And so what I'm going to do is I'm going to take the double integral over the region and multiply the integrand by x. It's still a double integral. I'm integrating with respect to x and y, but I'm weighting with respect to x. It's my weight. It's how much emphasis I'm putting on that particular point. All right? And then I can compute my y bar. My y bar is going to be the double integral, and you guessed it. I know you know what goes here. It's just going to be y times rho of xy dA. So that gives me my x bar and my y bar. And they actually call this the y moment and this the x moment, which I find very confusing. So I'm not even going to write that down. I'm just going to say that these are the moments. And so, I forgot. These are the moments, but they aren't the centers yet. Because remember, to get the center, we actually have to divide by the total mass. All right, those are the moments. To get the x bar, we're going to take this moment here and divide by, just like we did before, the total mass. So that's going to be this. And the y bar is going to be the moment for y divided by the total mass. That's the correct formula for x bar, y bar. Sorry, I forgot we have to divide by the total mass to get these. So what you do to do the problem, you find the total mass, you find the moments, and then you just divide. And that's how you get x bar, y bar.
Okay, so let's go ahead and do these computations. All right, so to compute the total mass, what we're going to do is we're going to do the double integral over this region of the density function, which is xy. And I'm going to do dy dx here. You could do it dx dy, but if we do it dy dx, then let's focus on the outer integral. It's with respect to x, so I need to specify what are the values that x is ranging from, or between. Well, x goes from 0 to 6, so those are my values on the outer integral. Now, what about the inner integral? That's y. So for every value of x, I need to think about, what does y go from? Well, it goes from 0, and it goes up to the height of this line. So I need an expression over here that gives me the height y of the line. Well, I can find the equation of the line. We can see the y-intercept is 3, and we can see the slope has to be -1/2 if it's going to come down here and intersect the x-axis at 6. So I know the equation for my line is 3 minus x over 2. Just basic algebra there. So that is the y value that gives me the height of the line above any given x. So that's exactly the height that I need to go to. 3 minus x over 2. So this is the double integral that we need to do. Let's go ahead and do the inner integral. So I'm going to anti-differentiate this. I'm going to evaluate it from 0 to 3 minus, x over 2. All right, and that thing will be the thing I'll integrate next. Okay, so when you plug in 3 minus x over 2 in for y and expand it out, you get, there's a little bit of work to be done there, but simple arithmetic and algebra will get you here. When you plug in 0 for y, well, you get 0. So this is what we get. All right, so there we go. Now we just have to anti-differentiate this with respect to x. And then we'll evaluate this from 0 to 6. Well, when you plug in 6, I'll let you do the details here. You'll get 27 halves. When you plug in 0, you get 0, so we subtract that off. We just get this. This is our mass. Okay, so that's the first part of the problem, was finding the mass. Now we can find the x bar and the y bar. Okay, now let's find our x bar. X bar is going to be the integral over the same region, so we'll have the same bounds here. But instead of just the density, I'm going to be multiplying the density times x. So I'm going to have x times the density. And then remember, to get the x bar, we have to divide by the total mass, which is what we just computed up here. So it's going to be divided by, this will just be 27 over 2. Now, I'm not going to go through the details here in this video. This is basic calculus computations that you can do on your own. Good exercise to do that. Please do that on your own. But you'll see, when you compute this out, you'll see you get 162 over 5. And like I said, we're dividing by the mass, which is 27 over 2. And when you do that computation and simplify it, you'll see you get 12/5. So that is our x bar. We can also compute the y bar. Y bar is going to be the double integral over the same region. But instead of multiplying by x, we're multiplying by y. And we divide by the total mass in the end. All right, well, in the numerator, what we're going to get is 81/5. And in the denominator, it's m, which we know is 27 halves again. And when you simplify this, you get simply 6/5. And so we have computed both our x bar and our y bar, and that is the center of mass. Our center of mass is a point, 12/5, 6/5. Let's just go look back at the picture and see where that is. Well, 12/5 is a little bit more than 2, so yeah, probably around here, and maybe even a little bit to the right of that point, maybe more like here. And 6/5 is a little bit more than 1, so maybe over here. So it looks like the center of mass, it's telling us, is right there. That's where we would balance this plate to balance it, make sure it doesn't tip any particular direction.